Okay, good morning everyone. Welcome to this special lecture concerning relativity. I am Armando Pisani. I teach math and physics to the high school Michelangelo Buonarroti in Monfalcone, Italy. And today I will present you a very short summary of what relativity is. It basically is physical principles that lead to its theory and some of the application if you have time enough to do that. Okay, let me first start by spending some few words about the research in physics at the beginning of the previous century, 20th century. Normally in London at the Academy of Science, by the fall of the year in December, the senior member of the Academy gives a talk concerning the status of the research at that time. At the very first year of the century, 1900, Lord Kelvin, which was the researcher who introduced the absolute scale of the temperature, concluded his speech by saying that the research in physics was over, that we have understood almost everything and just few tiny question marks remained. From these clouds at the horizon, the future bring some revolution in physics. So he was definitely wrong. Even if he was one of the cleverest scientists of the epoch, he was definitely wrong. Although he was correct by saying that those clouds at the horizon were problems to be fixed. The one, probably the major contribution to this revolution came from one person. Imagine that by the fall of the century, in 1999, the US Time magazine reports Albert Einstein as the most representative person of the 20th century. Moreover, the physics magazine Physics World indicates Einstein as the greatest physics ever. Why was it so? On the issue of New York Times in November the 7th, 1919, the paper declares that Einstein's theory triumphs over Newton's theory. At that very moment, that character, Einstein, becomes an international star. Stein was born at that time. By the way, you can see this at the bottom of the paper that theory was understandable by only 12 persons in the world. So it was quite hard to understand. That was the reason for the fact that Einstein did not receive any acknowledgement for the relativity. He won the Nobel Prize, but because of his studies on the photoelectric effect. Because relativity was too profound, too deep to accept. Okay? Now, who was this man? Let me introduce you the character, the person. Albert Einstein was born in March the 15th in 1879 in the small town in the south of Germany, which was called Ulm. His father, Hermann, was a middle-class merchant, which was not allowed to go to university because he was the second son of a family, and the first, his brother Jacob, was allowed to go to university, but the family was not able to afford the expenses to send both sons at the university. Well, the mother of Albert, Pauline, was has a high training in cultural context, so his formation was quite high, quite elevated, and this was important for the for the Albert education. She was very loved of music, and she urged Albert to learn how to play violin, and he played violin through all of his entire lifetime. Now you have some pictures of Einstein as a baby. You can see it on the left-hand side when he was 4, and he started speaking when he was 3, so quite late. And when he had something to say, he first repeats the sentence in his mind several times, and then he said it loudly so that the other people can understand. And it was quite an issue for his parents. Then at the age of 3, he had a sister, which name was Maria, but everybody called her Maya. Okay? No, probably the first milestones in the curriculum of Albert was when he was 5. His father showed him a compass, and this left a very deep mark in his formation, because he realized that there are something deeper than what you say. Nature is more profound than what it appears, and there was something mysterious that was worth investigating. Then also the connection with his uncle Jacob was very important, because Jacob also contributed to the formation of Albert by suggesting him several lectures. Here you have a picture when he was about 10 years, at the beginning of his attendance to the Luitpold Gymnasium in Munich. Probably the most relevant person in the formation of Albert was Max Talmey. It was a custom at that age, at that epoch, that a Jewish family host students that was not able to afford the expenses to attend the university. So the Einstein family hosted this student when he was a student in medicine. He was probably 20, and during his entire attendance to the lectures in University in Munich, and they gave him life support. So he had dinner, he had lunches with them, and he spent a lot of time with Albert. And he suggested Albert several readings, both concerning science, popular book in science, but also in philosophy. Imagine that at the age of 10, 11, Albert read by himself The Critique of Pure Reason by Immanuel Kant. And he had also several other books like the Euclid Geometry, and it was a very important reading in his formation. Okay, and soon, after a few years, Albert became so able, so smart in science that he overtook his mentor. But as a side effect, he did not feel very good at the educational system in school, so it suffered quite a lot. This is a key point in his evolution, his education, because by the suggestion given him by Max Talmey, he read the principle, the main works in ancient philosophy, mainly Greek philosophy, and he developed the idea, which was first suggested by the ancient philosopher Thales from the ancient Greek, that the complexity of the universe that you observe may be reconduced, may be explained by only one basic principle. For Thales it was water, but that doesn't matter. The main point is that you can comprehend, you can explain everything, the great complexity you observe, by one principle. And this is what the engine that works even today. Nowadays, research is the continuation of that idea. And in particular, Einstein spends the major part of his life by searching this theory, which nowadays we don't have. We have no single theory that explains everything. We have 3 different mechanisms that explain every phenomena we observe. The dream, the aim of theoretical research is to merge these 3 principles to have only one. Okay? And this is the crucial for his formation. Then, after an economical crisis in 1894, the Einstein family was forced to leave Munich, and they decided to move first to Milan and then to Pavia. because Albert's father worked with his uncle, with his brother Jacob, in a electrical devices farm. But at that epoch, Germany was already evolved, already electrified, while Italy was not. So they decided to move to Italy. And they decided that the best thing to do was to leave Albert in Munich in order for him to complete his studies. So they left, and Albert was left alone and he left with his aunt in Munich. But he was so, how to say, uncomfortable with the German education that at the end he decided to leave Munich and to reach his family in Italy. By the end of the year, he left, he took a train and went to Pavia to rejoin his family. The first thing he did was to go to his father and say, "Hey, Daddy, I don't want no longer to go to school. I will study by my own, and I will spend my time in studying at my own judgment." And he went to attend some lectures at the University of Pavia, but he spent a lot of time by his own, mainly by walking. Imagine that he went by walking from Pavia to Genova, which is a very long trip. Okay. Second point, I don't want no longer to be German. I reject German citizenship because he didn't want to serve in the army. Because in fact he compares the German education with the behavior that a soldier is subject within the army service. And at that time, the closest institution that accepts students without a high school diploma was the Polytechnic in Zurich, in Switzerland. So he decided to try to enroll at that university, and the result is that he failed. Okay. So the one of the teachers that was in the commission suggested Einstein to Albert to enroll at the final year of a high school in Switzerland, and then to try again to enroll to the University of Polytechnic in Zurich. He did so, so he was hosted by one of his teachers, and he had a very good time at that school. In particular, this quoted sentence comes from his autobiography, and he says that that school, the atmosphere was very relaxing and supporting students, and students and teachers did never use their authority to be obeyed or to train students. So he felt very well at that epoch. This is the final chart with the quotation marks you get in several subjects at the end of the school. So he took the exam, he was successful, and in September 1896, he was successfully admitted to the Zurich Polytechnic. Okay, he was 17. But the life at university, let's call it ATH, and the Polytechnic in Zurich was not very easy for Einstein, because he decided to go he rarely attended lectures. He preferred to go to the lab and do experiments. So he renounced to, in particular, to math lectures, and it was a very hard, this produced a very hard problems when he was a researcher several years later. At that epoch, he met his eventually the one who will eventually become his wife, which is Mileva marriage, and he met this girl at university because at that time, one girl who wanted to attend university has only two possibilities. Either she will go to Paris or to Zurich, because those university was the only one in Europe that allow girls to attend university. In no other university was possible for a girl to go to university. That was a really, really unhappy thing. And moreover, he met some other friends. We became friends for all his lifetime. One is Marcel Grossman from Hungary, and Michelangelo Besso from Trieste. But the relation with teachers at university was not that easy. In particular, the physics teacher of Einstein refers that Einstein was a clever student, very clever, but a very strong drawbacks. He didn't want him to teach him anything, because he criticized most of the things that the teacher says. So this is not a minor fact, because this causes a great problem to Albert when his curriculum was over. At the beginning of the 20th century, when he completed his course of studies, normally the university accepts students as supporting professors, as teachers. Okay, so for Albert there was no such possibility, because it was not easy to be controlled. He had a very hard time with his teachers, and they decided not to offer him a permanent position. So he had to move away, and he decided to seek a job in the high school as a temporary teacher. Finally, he found a permanent position by using the help of his friend Marcel Grossman at the patent office in Bern, Switzerland. It was a very nasty work, because very annoying, but it leaves Albert a huge amount of time to think and to work. And in that period, he didn't know English, he just speaks German. And he had no contact with university. He only can read papers and research and books just by the fact that his friends lend the paper to him. Okay, and he worked at home, or he thought to what he was working on at work, but basically he was isolated. And the help of his wife, which is, you can see here, Mileva Marit, was also important. Imagine that he was able to marry Mileva just after the death of his father, because the Albert family never gave him the permission to get married with Mileva, because first, she was not Jewish, and second, she had a problem when walking. He had a leg which is different from the other, so he has not a regular walking. So it was not allowed by the family to marry his wife. He could do it just after the death of his father. Well, within this situation, he was able to produce 3 different revolutions. On the year 1905, he published in the Annal of Physics 5 different papers concerning 3 topics. First, relativity theory, then photoelectric effect, which was worth the Nobel Prize in 1921, and then Brownian motion. The first, relativity, we'll speak today. The second, effect, gives support to the quantum theory, and the third paper was a milestone in the history of atomism, because after that work, no one had no longer any doubt concerning the existence of the atoms. So 3 crucial topics. Now, what about relativity? Relativity has something to do with motion. Now, if you look at this picture, you have no doubt that the bird is at rest. He is not moving. While here, you can see the baby, and you hardly doubt that the baby is moving. So apparently, the motion is absolute. Well, the first quotation concerning the relativity nature of motion dates back to Euclid in his work Optics. And Euclid said that if your eye sees something, then you have the impression that what you see is moving faster than what you move. If the speed is larger than yours, you see this thing go ahead. If you move at the same speed, you see the other thing at rest. And if the other object goes slower than what you move, then you see it go backwards. So this is the first statement that the nature of motion is essentially relative. It depends on who is describing the motion. The motion is not absolute. We have a small, I don't know if we have time to see, maybe yes. This is a short, now this is a crucial example. If you go on a ship and the ship moves at constant velocity, so constant rectilinear motion, then in an ideal situation where you have no movement, no shaking of the boat, everything you can do on the boat is exactly the same that you will observe if the boat was at standing still, no motion. This means that in a reference frame with this kind, moving at constant velocity, you can do no experiment in order that detect the effect of the motion. So the motion is only relative. This principle was very clear to Euclid, but think that Hypatia, which is in this movie, is the actress plays Hypatia. This is in the 5th century after Christ. So the lapse of time between Euclid and Hypatia is 8 centuries, and then the relativity of the motion was lost. It became renewed by the studies of Galilei. And he used the example of the boat, especially to claim this, that you have no way to distinguish two systems, two reference systems, one in motion relatively to the other at constant speed, at constant velocity. And this is the deepest principle in all the classical physics. By classical, I mean from Galileo and Newton. In fact, the nowadays foundation of the principle of classical relativity is based basically on the work of Isaac Newton with the trip principle of dynamics, which we had studied some years ago. Probably one of the most important consequences of this principle is the composition of velocities. Imagine this. Imagine you have a gun on a cart. If you fire the gun, then the bullet will move at a certain speed, no matter what it is. Let's call it VC. Okay? And if the cart is moving by relatively to, say, to the streets or to the railways, so to say, at a speed capital V, then if you are at rest with the railway, you will observe the bullet moving at a velocity which is the sum, the algebraic sum of both V, capital V, and VC. And this thing is very easy to prove, to measure, to experiment by doing measurements, no problem. But what happens if one of these objects is moving very, very fast? As the light. The light moves at 300,000 kilometers in 1 second. So it's very, very fast. If I do the same thing, and instead of having the gun and the bullet, I have a light ray. Imagine that this person turns on his pocket lamp. Then I will observe the light coming from the pocket lamp with respect to one person which is at rest on the earth. I will observe a velocity which is the sum of c, velocity of light, plus the velocity of the car, 15 meters per second. Is it so? Though, as the popular wisdom says, the proof is in the pudding. If you want to have an answer, you have to do an experiment. And these two persons, Michelson and Morley, devised a special equipment just to answer this question. Am I able to measure different velocity of lights in different reference frames? Well, the answer was no, you can't. Imagine that this null result experiment, they found nothing, was a nothing which was worth a Nobel Prize. They got the Nobel Prize just because they found nothing. So when we move to the lab and the student says, oh, I did the experiment, but I found nothing, I answer, then you may get the Nobel Prize because of that, because it already happened in the history. What did that occur? Well, refer to this example of the car. If the girl throws a rocket or a stone by a certain speed, then if I'm standing at rest on the street, I'll observe the sum of velocity of the rock plus the velocity of the car. While on the contrary, if I measure the velocity of light, I will measure the same number, I will get the same result, both if I measure light from the reference frame of the car or from the reference frame at rest with the street. There is no difference. I measure exactly the same value. So what is this meaning? The interpretation of this result took several years for several physicists, but the one who got the right answer was a forgotten employee of the patent office in Bern, Switzerland, who had a great advantage relative to all the others, because the one who did think by his own mind. And this is crucial. He had the bravery to propose something very simple but very deep. So Albert based his theory, including the former principle of relativity, which is the second law in this page, which is the law of physics, are all the same in all the inertial frames. And moreover, the universe is built up in such a way that you can no longer measure different velocity of light in different frames. So wherever you measure it, you will find always the same quantity. Technically, we say that speed of light is an invariant. It doesn't change. It's always the same in all inertial frames, no matter what is the velocity of the source of the lamp that emits light. What does this mean? If you include this principle that everything changes, you change the concept of time, space, energy, and mass. Let's pay attention to this first consequence. Lend me your ears and pay attention. Imagine that you observe two lights coming from these lamps, one on the left front side and on the left hand side in the wagon. And you have two persons observing the light. One observer B is at rest on the platform of the station, and another observer A is sitting in the wagon, which is moving towards the right hand side. Okay? Then, if it is true that the light has the same speed in both systems, then observer B will say light from lamp 1 and lamp 2 flashes at the same time, because observer B is reached by these arcs, indicates the wavefront of light. B is reached by light at the same time. So he judges the flashing of the light occurring at the same time, at exactly the same time. They are simultaneous. While observer A completely disagrees, because since she is moving on the right hand, okay, she meets the light coming from lamp number 2 in a time which is before the light coming from light number 1. So she says those two flashes are no way simultaneous. So simultaneity is relative. Two events that appears to be simultaneous in one system are no longer simultaneous in another. So simultaneity, that in physics previous to Albert Einstein with physics of Newton and Galilei, was an absolute. If you say that something is simultaneous in one system, then it is simultaneous no matter who watches that phenomenon. Within this new theory, simultaneity depends on who is describing it. It becomes relative. Okay? This is a crucial fact. If you didn't catch this, please tell me. I'll repeat. This is the first, in my opinion, very striking effect. Okay? This is due to the fact that the light speed is the same for both observers. Okay? But there are several other effects. Imagine that you build up a particular watch. You observe the same phenomenon from a spaceship and from the Earth. Imagine the astronaut which is devising this particular system. There is a light bulb here, a light source, and it turns up, it flashes the light, and the light goes upward, it is reflected by the mirror and comes back to a detector, to a receiver. And you measure the times elapsed since the flashes of light and the return of the light reflected by the mirror. Then this time is the time to go and back of the signal. But if you observe the same process from the Earth, you will see the light making a much longer path. This distance is no longer d, but is d adjoined, we must add by the Pythagoras theorem the vertical distance between the lamp and the mirror plus the distance that the starship moves while the light is traveling. So the light is emitted here, it reflects in this position, and it turns back in this position. So if the speed of light is the same, and the path is longer, then the time for the go and back is much longer. So even the tick-tock of my watch is changed if I'm moving. So the elapse of time in the two systems does differ. The time flows at a different rate in different systems. The duration of a process is no longer an invariant. The measurement of a process depends if you observe it when it is at rest or if you observe it when it is moving. This changes very deeply. Okay? This is extremely new. That was the fact because Einstein did not receive the Nobel Prize for Relativity. It was very, very hard to accept this because at that time there was no technology able to prove this. It became much later. In fact, the first proof, one of the first proof of this was concerning cosmic rays. One of the highest, best expert of cosmic rays was an Italian researcher, which is Mario Rossi, who works at MIT in Boston, USA. And these cosmic rays are a particle coming from space and colliding with the upper state layer of the atmosphere. They produce particles that do change, they do decay. These particles have a very tiny amount of light. They decay in something like 10 to the minus 6 seconds, nanoseconds. But if there was no time dilatation effect, they would travel roughly 500 meters before decaying. But since they move very fast, they move at 99.5% to the speed of light. They are very high velocity particles. The time dilatation in our system, we observe them moving, the time they live is much longer, so they are able to cross the entire atmosphere and we can detect them on the surface of the Earth. That could not happen if there was no relativistic effect in time dilatation. This is one, and this experiment, this conclusion dates back to the 1941, so 36 years after relativity was proposed. Moreover, and I go quite quickly on this, if the time does expands the time dilatation, this is compensated by the contraction of length. Along the direction of the motion, imagine that we have a cosmic ray here, a particle moving very fast towards that cloud. Then in the system where the particle is at rest, all the distance along the direction of motion are contracted. They shrink, they are smaller. So the time dilates and the length shrinks, okay? It is not hard to prove this, but I will skip mathematical details. I'll just tell you that within the same framework, due to the fact that the velocity of light is the same in every frame of reference, you have both time dilatation and length contraction. One of the most well-known paradoxes connected to this is the twin paradox. Imagine you have two brothers, two twins. They have same birthday, but one of them decided to move, to make a travel on a starship at the speed of light, okay? But when he moves, this time goes much lower, and when he comes back, the one which remains on the edge is much older than the other, okay? And this was measured. We had several electronic watches, clocks, one at rest in the Earth, the other was put on the airplane. It was make the turn of the entire planet several times. And you see here the difference in the time counted by the two clocks is result to be definitely different. The difference is not very high, but it is measurable. So the effect is real. Okay, now you skip this. Another consequence is that, according to the principle of relativity, then mass and energy are equivalent. They are the same thing. They are connected by this factor, which is c squared. Okay? It was like if we measure the length in meters or feet. You measure the same thing, but in different units. Okay? And you can see here that as I approaches the velocity of light, the energy and the mass diverge. You have a vertical asymptote there. Okay? And this is the explanation. You see here, how much energy do you need to move something at the speed of light? If you take the limit of this expression as v approaches c, then you have this quantity goes to 0, and this quantity diverges. It becomes infinite. So even if you take a very tiny particle, an electron, you have no way to make it move at the speed of light, because the entire energy of the universe is not enough to give that electron the speed of light. Okay? The conversion, the equivalence between mass and energy, is the process that powers the stars. Within the stars, small particles, hydrogen particles, merge together to form helium. And the difference in masses is converted in energy and give us light and heat. While the opposite effect, you have a huge atom, an uranium atom, you break them in two by using very fast neutrons, then the remaining part of that bullet have a different mass comparing to the original target, and the difference is converted in energy. Is what we call fission, which means division, separation. Okay? So the general theory of relativity changes a lot of our life. Let me move quickly to the general theory of relativity, which is the theory that includes the one which is the previous we discussed up to now, and refers also to non-inertial frames. The basic principle of this part of the theory says that if I have a system which is accelerated, like a rocket sent into space, and I have a system at rest on the Earth, okay, then those systems are equivalent. This means that gravity is equivalent to an acceleration. This means that gravity is bending the space-time. If I had no mass here at the center of my system, and I send it something into space, it will travel through a straight line, okay? It will travel along a straight line. If I put a mass here, then the object make a bend, is curved, it follows a curved trajectory, not because it's feeling a force, but just because the geometry of the space-time is bent due to the effect of the presence of that mass. In this sense, we say that gravity bends space-time. The space-time is curved by gravity. Okay, we have a video that illustrates this, but we have no time to go into that. And if you have a dramatic deformation of this, is what you have when you say you have a black hole, which produces a discontinuity, a deep discontinuity in space-time. So something can approach the hole, but never come back. Okay? One of the first applications of this, of the general theory of relativity, is something that you all have in your pocket. This device doesn't work without relativity. The G.P.S. system, the global positioning system, is built up by using several satellites orbiting around the Earth. And if I do not take into account relativity, this fails in indicating my correct position by several kilometers. When this system was proposed by the US Navy during the 60s, the military person did not believe that that was real, and they devised two electronics on the satellites. One electronic taking into account relativity, and the other did not. Well, it turns out that the devices not taking into account relativity was wrong by several kilometers. No, the question is there anything in this room that is working due to gravity, due to relativity? The answer is, of course, we have all in our pockets. Okay? But I will skip the other applications, and I'll conclude by saying that in order to change the very basic concept of mass, space, time, and energy, you need to think by your own mind. You have to think differently, to discuss what the tradition suggests you, and be so brave to defend your ideas. Okay? And let me quote finally this sentence by Albert, which says that the most beautiful thing we have is the sense of mystery. There's something that you, at the first time, you don't comprehend, but deserves further investigation. And this is the source of the very deep science and both art and science are the effort of humankind to understand mystery. Only the tools are different, but the aim is the same. Thank you for your attention. Bye-bye.